So I've got a statement here. This is a cubic polynomial. Any cubic polynomial has a graph, as I said, that looks like an x cubed, either coming up like this or coming up like this, because for big positive and big negative x, the x cubed will have different signs and will be huge, right? And you can't go from negative to positive or positive, well, negative to positive or positive to negative, okay? I'm trying to do this the way you see it, without passing through zero, okay? That's something called the intermediate value theorem that we'll look at kind of formally before too long, okay? Not too formal. You don't want to over-formal it. So when you divide x minus z into ax cubed, etc., isn't it obvious that your first term is going to be like ax squared? It certainly will be after you've done a couple of long divisions, okay? You're going to have an ax squared, and there are many reasons for that. So that means that what you get as your quotient is going to be quadratic. It's going to be an ax squared plus something times x plus a constant number, right? So it will give you a linear times a quadratic. So the form is linear times quadratic. Now, what can you tell me about a quadratic? Do quadratics always have zeros? No. You've seen many that don't. You know, the vertex could be above the axis and the thing could open upwards. The vertex could be below the axis and it could open downward, right? In which case it would have no zeros. Okay? If it does have zeros, that means it can be factored. Okay? If you divide that quadratic by x minus one of its zeros, you'll get an x minus another zero. Okay? So this quadratic could be a product of two linear factors like this one, right? Okay? Or not, because it might not have zeros, right? So when you have a cubic equation, it's either the form linear times linear times linear with three zeros, right? Or it's of the form linear times an irreducible quadratic, meaning a quadratic that doesn't have any zeros. Okay? And that's a big deal. It's actually, the reason that's true isn't hard to reason out for cubic equations, but the actual reason it's true is something that mathematics majors at good universities get, maybe in their junior, but probably in their senior year. It's the fundamental theorem of algebra, okay? I think I ran into it in my junior year, but it might have been my senior, probably was my senior year, okay? And once you get, of course, an abstract algebra, which is really kind of a hairy course, it's not that hard of a proof, but before that you can't prove it. You don't know why it's true. You just accept that it is, okay? Anybody completed a good course in abstract algebra? Anybody got any hidden math majors in here? You know, met people with bachelor's degrees in math from good schools? Yeah, some of you have looks on your face like you might be. You kind of grinning. Okay, well, so I'm not going to explain it any further than that. I'll just summarize it, okay?